The work of Nobel Prize has transformed our understanding of the world. While approaching the Nobel Prize winners in chemistry, we not only learn their achievements, but also the spirit of honesty, tenacity, innovation, and forging ahead.
Hello everyone, welcome to today's class, the Nobel Prize winner in chemistry. 同学们你们好，欢迎走进今天的课堂，化学诺贝尔奖得主。今天会给大家介绍神奇的手性催化反应之父夏普莱斯。Today I will introduce to you a famous scientist whose name is Barry Sharpless for the magical chemical catalysis reaction. When you look at your left and right hands, they look the same, but they cannot overlap with each other. We call it as chirality. This is a kind of molecule called Chiral molecules. They refer to molecules with certain configuration or conformations which are different from their mirror images and cannot overlap with each other. The word chirality origins from the Greek word chiral. From the space science to earth science, from chemistry to biology, chirality can be found almost everywhere. As celestial bodies in solar system rotate in the right-handed direction, which is called right-handed rule. Chirality is also an important morphological feature in botany. Most climbing plants twine to the right along the trunk, but few twist to the left. The more common directions in sailfish is to rotate to the right, but some kinds of shells, as the glowing conch on the Atlantic coast, generally rotate to the left. So today's leading role is one of the scientists who have won the Nobel Prize in chemistry for chiral synthesis in 2001. His name is Barry Sharpless. Barry Sharpless won the Nobel Prize in chemistry in 2001. He was born in Philadelphia of the United States. He worked for the Scripps Research Institute in USA. His prize motivation was for his work on catalytic oxidation reactions. Many molecules appear in two different reverse forms that have different chemical biological effects. Through spatial catalysts, which are substances that facilitate chemical reaction without being consumed in them, it's possible to bring about a process in which only one of the reversed form is produced. In the 1970s, Barry Sharpless began developing methods for using catalysts with such properties during oxidation reactions. Among the other things, it has enabled production of various types of medication. Comparing selectivity as the bench with selectivities in living systems remains striking. For example here, the squalene monooxidase in our liver's property deposits a single oxygen atom on the squalene molecule and in doing so, further only chooses the terminal double bond as shown in the screen here. On the other hand, the attempted asymmetric I-oxidation is also called as AD from a single bond of squalene does give the terminal dions in 96%. How does he think about the chiral catalytic reaction? Let's see what did Sharpless say during his Nobel Prize winner lecture.
Yeah, this is a quote from Orville Chapman. He likes to say things in a very strong way, but I think he's got a good point here. And I also bring it up because I would like to get one of Banks' pictures of Van Hoff, but maybe I can arrange to suck that out of your computer sometime. But Van Hoff being the man along with Lebel who started the journey into three-dimensional carbon.
Nature's enzymes made it possible to imagine simpler asymmetric catalysis. What we found, however, was unimaginable on two scales. Small, highly elastroselective catalysis that were not only fettered by nature lock-and-key modus operandi, but tolerant as well substance through our entire range of olefin substitution patterns. You may wonder why the chirality is so important. People constantly find that there's a chiral environment in organism. The pharmacodynamic of drugs and pesticides action on organism are mostly related to chiral matching and chirality between them and target molecule in body. Therefore, a research of chiral drugs and chiral pesticides is particularly important. Many of the drugs used for treatment are chiral molecules. Different enantiomer of chiral drugs show different pharmacodynamics in physical process, especially when enantiomer of chiral drugs is effective for treatment, but the other is harmful. The strategy of thalidomide in the 1960s is a prominent example. Later study found that only its R isomer has a sediment effect than the racemic thalidomide, where its S isomer had tetrostatic effect. In just 4 years, more than 12,000 deformed sea babies were born worldwide because their moms took this pill while pregnancy. These painful lessons have made people realize that chiral drugs must be carefully treated by examining their two isomers separately. Because human beings are living organisms composed of all amino acids, they cannot metabolize right-handed molecules very well. Therefore, the consumption of drugs containing dextrin molecules will become a burden and even cause damage of life. Chiral synthesis is a very active field in chiral technology, especially in chiral catalysis reaction. North, Sharpless, and Laurel 3 Nobel Prize winners have found a series of chiral catalytic hydrolation and chiral catalytic oxidation reaction after more than 10 years of research. The hydrogenation and oxidation catalyzed by transition metals have not only brought chiral synthesis into a new stage of development, but also been applied in industrial production. Chiral catalysts are catalysts containing chiral carbon atoms, which play an important role in some synthetic reactions. For example here, the Banab chiral catalyst developed by Nouri, one of the 2001 Nobel Prize winners. The complexes are Banab with metal rhodium and ruthenium have been proved to be efficient catalysts for many prochiral olefins and ketones. We have talked about many chiral molecules and chiral reactions today, which were discovered by Professor Sharpless and other scientists. I hope you have learned a lot from it. Thank you.
大家好，法国化学家巴斯顿说过，所有生物物种在其结构上，在其外部形态上，究其本源，都是宇宙非对称的产物。20世纪60年代的反应瓶悲剧是一个突出的例子。仅仅4年时间，世界范围内诞生了1.2万多名畸形的海豹婴儿。惨痛的教训使人们认识到，手性药物必须对它的2个异构体进行分别考察。手性催化研究在过去几十年中已经取得了巨大的成功，但总体而言，实用和高效的手性催化合成方法依然处于发展的最初阶段。 真正在手性工业合成中得到的应用技术还十分有限。未来的合成化学必须是经济的、安全的、环境友好的化学，即以100%的选择性和100%的收率，只生成需要的产物，而没有废物产生。手性催化合成作为实现完美合成化学的重要途径之一，目前还有许多科学问题有待解决。因此，要实现手性催化反应的高选择性、高效率，需要从基础研究入手，通过理论、概念和方法的创新，解决这一挑战性问题。好了，本次课到此结束，谢谢大家，再见。